ABC, and I'm connecting these points in such a way that ABC is an equilateral triangle. It implies that ABC is a triangle. Is it true? ABC is an equilateral triangle. It implies that ABC itself must be a triangle. ABC is an equilateral triangle. It means, or it implies that ABC itself must be a triangle. Obviously,
Yes.
if you are talking about something equilateral and it's a triangle, then it must be a triangle. Okay. Is this thing true? ABC is a triangle. It implies that ABC is an equilateral triangle.
Yes, sir.
ABC is a triangle. It must imply that ABC is an equilateral triangle. I think it is not necessary.
Not necessary.
It is not necessary.
Not necessary.
But the above statement is true. That ABC is an equilateral triangle. An equilateral triangle means all the sides, three sides are equal. Then obviously it must be a triangle. If it is a triangle, then it will be an equilateral triangle. How is it possible that it is not necessary without that? Okay, so in these two implications, we can deduce one thing, that a triangle, there is a triangle ABC, it does not imply that it is an equilateral triangle. But for equilateral, it must be a triangle. It must be a triangle. So whenever you take any of this implication, the statement before this is always called sufficient, and after this is always called necessary. So in A implies B is a sufficient condition, whereas B is a necessary condition. Whenever this particular thing is asked, that in an implication which one is sufficient condition and which one is necessary condition, so always your hypothesis part is sufficient and your conclusion part is necessary. You have to take this example. If I am giving you an equilateral triangle, then you can always say that this is going to be a triangle. Okay?
Yes.
Because this condition is sufficient. Sufficient means if I am giving you that information, you don't need any extra information to conclude something. You will say that, okay, you gave me this information, I will deduce this thing easily. And this is deducible. So this condition is called sufficient. But if ABC is a triangle, then it does not imply that it is an equilateral triangle. But for an equilateral triangle, it must be a triangle first. Then for this triangle, I need some extra conditions. So for an equilateral triangle, being a triangle is a necessary condition, but it is not sufficient. So sufficient means I give you this information, you can easily deduce this information. But if I give you this information, you are unable to complete this information, but this is a main pillar and main part of that. Without this thing, that is impossible. Then we call this condition to be necessary. Means without triangle, you can't conclude it is going to be equilateral. But being a triangle does not imply that it is equilateral. Means this condition is very much important, but as a whole, it does not imply this thing. As a whole, but this is necessary. If I give you this information, it is sufficient, it is totally okay that you don't need any other information and you can conclude this thing. So in any implication, you just keep one thing in your mind, this part is called sufficient and this part is called necessary. These questions might be asked in any examination whenever you are going to appear. And the other thing that we discuss is converse and contrapositive of a statement. Let us come to the point. What do you mean by a biconditional statement, and what do you mean by logical equivalence? So, a biconditional statement is a statement of this form. And what does this statement mean? That A implies B and B implies A. So whenever this happens, that statement A implies statement B and statement B implies statement A, we concisely write this particular thing in this way, and we call these statements to be biconditional statements. And when these are true, like A and B are true and A implies B and B implies A, we call these sentences to be logically equivalent. So statement A and statement B are going to be logically equivalent, and we write these to be A is equivalent to B. Whenever A implies B and B implies A, and both are true statements, we call these to be logically equivalent statements. This is going to be the very much important thing, because in some of the theorems you are only given one side, okay? This particular statement implies this statement. But in some statements or in some implications, the reverse is also true. We say that A implies B and B implies A. And we call these statements to be logically equivalent if those are true. What should be the truth table for this? Like we made truth table for A and B, A or B, A implies B and B implies A. We can make all these truth tables easily. But the question is, how can we make truth table for A implies B? You know very well that I need some preliminary information like A and B. What are the possibilities? True and true, true and false, and false and true, and false and false. One thing is that this is always true when both are true, this is always true when both are false. Because you know very well that a true statement implies true. You will take both sides. A implies B, true implies true. B implies A, true implies true. Always true. So an implication is true if both are true, we know very well. And an implication is true always when both are false. Because a false statement implies false statement, and on the reverse side a false statement implies false statement. What should be the other things?
False. False.
Both false?
Yes.
And what's the reason?
True implies false. How this is not making a sense?
So the main thing is that this does not make sense. We know very well. True statement implies false statement. So this is false. Why this thing is false?
Reverse.
Yes. Since we have to see both directions,
Yes, sir.
the direction false implies true is okay,
Okay.
but true implies false is not okay. So this is going to be false. So this double implication is okay when both are true and both are false. But we are mainly concerned with, whenever we are proving theorems, we are concerned with when both statements are true. Then in these statements, you have to always prove two sides. First you have to prove A implies B, and then you have to prove B implies A. If you are going to take only one side, it means you have done the half of the proof of the theorem and it's not complete. We will be coming to this whenever we are going to prove these theorems and different ways to do this. There are some sort of laws of logical equivalence that I'm going to mention with you, but I'll be sharing this page with you. So I'm going to discuss only some of these. The commutative law would be, you know very well that in some other terminologies like union and intersection, we know very well A union B is equivalent to B union A intersection B is B intersection A. So similarly we have A and B is equivalent to B and A. A or B is equivalent to B or A. So this is called the commutative law or commutative property of these connectives. One is AND and another is OR. And there are other distributive laws, idempotent laws, De Morgan's laws that we can discuss so far. There are some inverse laws as well. How about this? A and negation of A. I think we discussed this thing. Yes. But we discussed this thing in the case of contradiction, that this statement is always false. So A and negation of A is always false. And A or negation of A is always true. And we can also discuss some identity laws, like when you take A and any true statement, the result is always
A.
True or A? Yes, it should be A. Equivalent to A. Why it is the case it is? Because when A is true, this whole will be true. When A is false, this will be false. Because false and true, the condition is and, so it becomes false. So these are logically equivalent, and we call this law to be identity law. Because you know very well in identity, like you add 0, the result becomes same. You multiply 1, the result becomes same. But here addition and subtraction is replaced by conjunction and disjunction and an or. And the identity is true and false, so you are going to apply that particular thing to get these results. Okay, so I'm not going to make this whole list because it will take a lot of time and we have to move ahead. Now, the next thing is that what quantifiers do we have and how to negate the quantifiers. Because whenever we are going to prove a statement, we always, whenever we are applying contrapositive method, we negate the statements. And if a statement contains some sort of quantifiers, then we must know that how to negate those. But the first thing is that what is a quantifier?
सर करंट इस ब्लू बार का यूज किया वो ग्रीन जो का
जी
Quantify the things. Quantity.
Yes. So quantifiers, the first is called the Universal Quantifier, and we denote it with this inverted A. So this is simply A, but it is inverted, and we call this the Universal Quantifier. So if you see this word, quantifier is related to quantify or quantity. It means it basically tests the quantity of something. And you can see the word universal, it means it must be applied to the set or all the elements which are inside a particular set which we are concerned with.
Under consideration.
Yes, under consideration whatever elements we are taking all of them. So this is called the universal quantifier, and we denote it with this symbol. What is going to be the example for this? So we always say for all x, and sometimes if our set under consideration is real numbers or natural numbers, we do not write anything after for all x. Whenever you say for all x, it means you are talking about all the real numbers. And whenever you are saying that for all x and you are talking about integers, it means you are talking about all the integers. So it depends upon what context you are studying. If the context is not mentioned, then you always write for all x which are going to be part of a certain set, let's say real numbers or natural numbers. It means that you have to pick all the elements from the set of real numbers, and then I give you additional condition. Sometimes the additional condition is written after comma. For all x, let's say p of x holds, and p of x is a certain condition. We are coming to that, what does it mean. And sometimes it is written in this way, for all x, and you write that condition inside this bracket. Sometimes you write after comma, and sometimes you write after inside that parenthesis. It means this condition is true, or this condition holds whenever you take each and every element from this particular set. Each and every is basically quantified by this symbol. For all means you have to take the elements from this set of real numbers, and specifically all the elements. Okay, any example? For all x in the set of real numbers, x square is always greater than or equal to 0. So you take any real number, you square it, the result is always going to be greater than or equal to 0.
So now we are p of x.
Yes, this is p of x. This is condition p of x, and this p of x holds for all of these elements. You can either write these parentheses, either you can write in this way after comma. It doesn't make any difference. Okay. Now I have a statement, and I am going to write that statement using these quantifiers. The statement is for all. Now I am going to tell you that statement in English. For all rational numbers x and y, the product xy and x plus y are rational. So the first statement that I am going to tell must be quantified, and the second statement is the condition p of x. So for all rational numbers x and y. So how can I write this? For all x comma y in the set of, I can write this in this way as well. For all x in q and y in q. This is also okay. Now you have to write the condition p of x. P of x means x, y, and x plus y are also rational. So how can I write?
X.
So x, y belongs to rational, and
X plus Y also belongs to rational.
also belongs to rational. So you may specify with this and, or you can give comma, or you can precisely write like this thing, like x comma xy comma x plus y belongs to rational number.
Alright.
But this p of x must hold for each and every x and y in this set q. So we must know that this inverted a means for all, and we call this the universal quantifier. The another is called the existential quantifier. So let me write it here. And we denote it with this symbol. There exists. And we read it there exists, we read it for all. So this is called the existential. Okay. So the existential quantifier. So what does it mean? It does not mean that some p of x holds for each and every value, but it means that
At least
there exists at least one or some x, such that for those x, for that particular x, or for those all x, that statement is true, but not for all the elements in that particular set. So let me write what does it mean. So there exists x in the set of reals or whatever, p of x holds. What does it mean? One thing is that there there exists nx माना कम से कम हिकड़ी x जरूर exist कंदी such that p of x holds or p of x is true. If I only write p of x, it means p of x holds. Number 2, for some x, p of x. For some x means there exists some x. It can be 1, it can be 2, but not for all. P of x means p of x holds. Number 3, there is some x. It is same as this. There is some x such that for those x, p of x holds. So these are two quantifiers, what we call them, the existential quantifier and the universal quantifier. Statement we can write universal and existential quantifiers together. I am giving you some examples for that, and then you have to tell me what that particular statement means. So for all x in the set of integers, there exists y in the set of integers such that y is greater than x. What does it mean?
There exists some number in integer which is greater than x. So in integers, x and y both are belongs to integer. But in integers we can compare that some integers are greater than other integers.
For all x in integers, it means the first thing is that you have to take any integer. Up to here, for all x means you have to choose any integer. 2, 3, 5, 7, minus 1, whatever. For that integer, there must exist some another integer. So I am choosing an integer, and this condition tells that you may choose any, whatever you want. So let's choose 3. For this, there must exist another integer.
Which is higher than
Now this condition depends upon this, such that this integer will be greater than the chosen integer that you have chosen already. Now what should be this integer?
4.
This can be any integer, but always greater than 3.
3.
It means this particular condition depends upon this. For all x, you have chosen. For all means you can choose any, whatever you want. There must exist another integer such that this condition holds. Okay, one thing is that if I change the order of these quantifiers, then what does it mean, and will the statement be still true or not? Order means I am going to write this thing as for all there exists y in z, and for all x in z such that y is greater than x. What does it mean? And the question is it true or not? This is the main thing. Then we will be able to decide that whether we can change the order of the quantifiers or not. Or changing the order of the quantifiers is okay, or we can't do that. This is something very much important.
this will not be
Not
true.
because y is fixed.
Y is fixed. It means there exists y, and there exists y means there must exist some particular y. That let us choose that particular y, whatever it is. Then for all x that must be true. It is not possible. It is not possible that for all x the condition must be true.
In x way a variety.
There will be some x. If you say for all x, this is very problematic. Because there will be some x which will be greater than your chosen number. There will be some x which will be less than or greater than or equal to your chosen number. So this particular condition is not true, and this condition does not mean this condition. So it means you are not allowed to change the order of these quantifiers. They play a crucial role in this. Now the thing is that if you are given a statement, mathematical, this is mathematical statement, this is mathematical statement, this is mathematical statement, and from the very beginning we are discussing how to negate a statement. Negate in English means just make negative. Affirmative becomes negative. But how to negate a statement that contains a quantifier?
Yes.
You have a statement that contains some sort of quantifier. How can you negate that statement?
So for all and there exists, these both are just like antinomious actually.
Yes. But again, we have to discuss why. For all x in R, x square is greater than or equal to 0. We all believe that this statement is true. You take any real number, whether it is positive or negative, you square it, the result is always going to be greater than or equal to 0. Now, I am going to negate this statement, and if we believe this statement is okay, then its negation will always be false. Negation will always be false. But the question is how to negate a statement that contains some sort of quantifiers.
There exists an X. There exists.
Whenever you negate this statement, you always negate this for all to
There
exists. It means this is whole statement and I am going to negate it. Negation, it means I am going to make it negative, in other words. So this for all becomes there exists, and this particular P of X is inverted. If this is greater than or equal, this becomes less than. Now if this is true,
then this is exactly false.
if this is true, then this must be false. Is this false?
Yes. For sure.
It means I just assure you one thing. I can give you a real number. There exists X means I can give you one real number such that its square is going to be less than 0. You will never believe me. So you take any real number, you square it, you will never get a negative number. It means this statement is always false. So you must understand that how to negate a statement which contains some sort of quantifier. So how to negate? Just let me write it precisely. If you have for all x, P of x, and you are going to negate this, what you will do, for all becomes there exists, and this P of x is negated. Means if this is greater than or equal to 0, this becomes less than 0. And if you want to negate this statement, then this there exists becomes for all x, and this becomes negation of P of x. So this is how you do the negation of the quantifiers when some statements that contain quantifiers are given to you. And this is something very easy. For all becomes there exists becomes for all, and the inside statement must be negated. Negated means in mathematics if it is less than or equal to 0, it becomes greater than 0. If it is equal to, it becomes not equal to. If it belongs to, it becomes does not belong to. So the inside statement is negated as well. You can also negate a statement which contains both quantifiers. So in both, like for all becomes there exists becomes for all, and your P of x is going to be negated. So you can negate some statements like this as well. But why these are necessary, it will come to know when we are going to prove different theorems. Okay, so let me give you a statement, and I want you to tell me its, or just write down its negation. The statement is a bit simple. For all x in integers, there exists y now star, and I think r star means the set of non-negative reals or positive reals. This one means, okay, whatever, we are not concerned about this. xy is less than 1. This means the set of real numbers excluding 0. Excluding 0. Because when 0 is here, this is 0, then x will be undefined. X will be undefined because s will be less than 1 over 0, which is undefined. So whatever I want, its negation. It means I want you to negate this. So what should be answer?
There exists
There exists x in z
the
for all y r star.
Greater than 1.
xy is
greater than 1.
Or equal to.
greater than or equal to.
Yes, sir.
Greater than or equal to. Because equality or condition को खत्म किया नहीं. So the negation would be there exists x in z for all y or star.
xy greater than or equal to.
xy is greater than or equal to 1. If this is true, this is obviously false. If this is true, this is false. If this is true, this is false.
This is false. Yes, sir.
Always.